All right, this is a tough question. It is based on this concept of first a unit cell and then second the density equation. So if we're looking at density equals number of atoms, and that's based on the type of unit cell, and this one is a face-centered. And then we have molar mass and edge length cubed, and then Avogadro's number. Now, this one's a little bit different because we don't have density and we don't need molar mass because we're given this molar volume. So I'll show you how we convert that. First thing, let's look at this face-centered structure. So face-centered is this unit cell that has 1/8 of an atom on each corner, and then one on each face, which is a little hard to draw. And so we do need to count how many atoms we have. And so we have 1/8 from each one on the corner, and there's 8 of them. So that's one total atom within the unit cell. And then the 6 face ones is a half. So half of it is in this unit cell, half is in another unit cell. And there's 6 of them, so that's 3 more atoms. So there's 4 atoms total in this unit cell. Now, this one is a radius question. So even though we're given some information, we will have to solve for A, and then with an FCC or a face-centered cell, A is equal to 2 square root of 2R. So we will have to use that at the end and rearrange. Once we know A, we can solve for R. Okay, so first thing I'm going to do is rearrange this density equation, kind of see what we have. What we need to do is solve for A. And so typically we would rearrange it and it would look like this. Density over, so number of atoms times molar mass over density times Avogadro's number. But what we see is these two numbers here combined, molar mass over density is equal to grams per mole and grams per centimeter cubed. Those combined are what we call the molar volume, because here grams would cancel. And so we have, this would come up over the top since it's on the bottom. So we have centimeters cubed per mole. And that's what we're given right here. So these two are combined. And so what we have is A cubed equals the molar volume times the number of atoms over Avogadro's number. So we plug those in. We got this 18. And what we want to come away with is this centimeters cubed, because that's the volume we need. Now we multiply by the 4 atoms. And then on the bottom, we know that there are 6.02 times 10 to the 23rd atoms per mole. So we cancel all units and we get, plug that into the calculator, we get 1.196 times 10 to the minus 22nd centimeters cubed. Tiny, tiny number. But we need to find A. So the way we find A is raise it to the 1/3 power. So we're going to raise that to the 1/3 power, and we get 4.926 times 10 to the minus 8th centimeters. Now, it asks for the answer in picometers, so the next thing I'm going to do is convert that to picometers. First thing I'm going to do is convert to centimeters, so out of centimeters to meters, 100 to 1. And then I'm told up here that for every 1 meter, there's 1 times 10 to the 12th picometers. So my centimeters divided by 100 times 1 times 10 to the 12th, and I get 492.6 picometers. And then finally, I'm going to rearrange. So R is equal to A. So 492.6 divided by 2 square root of 2 or square root of 8. And that gives me 174 picometers. So tricky problem based on this idea of density, but kind of one step further. And the key thing here is following the units. So I was able to see that molar volume is a combination of the molar mass and the density. And so we were able to rearrange that equation and use it to solve for A, which then we could solve for R of these atoms. And in this case, we get 174 picometers. We'll check that out. And there we go. So you can see the work that Aktiv does here. Okay, so key to know that it's FCC and that we're solving using this density type equation, but rearranged a little differently.